Grounding a radio tower on a rocky ridge with shallow soil presents a unique challenge. Here are several grounding design options to consider. Firstly, a radial grounding system can be implemented. Install 8 to 10 copper-clad steel ground rods around the base of the tower, spaced 20 to 30 feet apart. Connect the ground rods to each other using bare copper wire, with a minimum size of number 6 American wire gauge, AUG. Extend the radial wires out from the tower as far as possible, ideally to a distance equal to the height of the tower. Secondly, a ring grounding system is another option. Excavate a trench around the base of the tower, 6 to 8 inches deep and 18 to 24 inches wide. Place bare copper wire, with a minimum size of number 4 American wire gauge, AUG, in the trench and connect it to the tower's grounding system. Backfill the trench with conductive material such as crushed limestone or bentonite. Thirdly, a plate grounding system can be used. Excavate a hole 6 to 8 feet deep and 4 to 6 feet wide near the base of the tower. Place a galvanized steel or copper plate with a minimum thickness of 1/4 inch in the hole. Connect the plate to the tower's grounding system using multiple copper wires with a minimum size of number 6 American wire gauge, AUG. Backfill the hole with conductive material. Fourthly, you can use grounding rods with extension electrodes. Install copper-clad steel ground rods, as in the radial grounding system. Attach extension electrodes, which can be copper rods or tape, to the ground rods using specialized connectors. Bury the extension electrodes horizontally in the shallow soil above the rock base to increase the effective grounding area. Fifthly, consider chemical soil enhancement. If the soil is particularly rocky or non-conductive, consider treating it with a chemical soil enhancement. These products can improve the soil's conductivity and reduce the overall grounding resistance. Sixthly, multiple grounding methods can be combined to create a robust and reliable grounding system. A combination of radial wires, a ring ground, and a plate ground can provide redundancy and enhance grounding effectiveness. Several additional considerations are important. Use high-quality materials, such as copper-clad steel or galvanizing, to ensure corrosion resistance and longevity. Test the grounding system periodically to verify its integrity and resistance to ground. It's also important to consult with a qualified grounding expert for specific design recommendations based on site conditions. The goal of any grounding system is to provide a low impedance path for fault currents to return to the source. This helps to ensure the safety of personnel and equipment. In situations with shallow soil and rocky conditions, achieving a low grounding resistance can be challenging. However, by carefully considering the factors discussed, you can design an effective grounding system for a radio tower on a rocky ridge. The choice of grounding method, or a combination of methods, will depend on several factors, including the size and height of the tower, the soil resistivity, and the available space. A thorough site assessment is essential to determine the best approach. Soil resistivity is a measure of how well the soil conducts electricity. High soil resistivity makes it difficult to achieve a low grounding resistance. Soil resistivity can be measured using a soil resistivity meter. The results of the soil resistivity test will help you determine the appropriate grounding method and the number and length of ground rods or plates needed. The size and height of the tower will also affect the grounding design. Larger and taller towers require more extensive grounding systems. The available space around the tower may also limit the choice of grounding methods. For example, if there is not enough space to install a radial grounding system, a ring ground or plate ground may be a better option. Chemical soil enhancement can be used to reduce soil resistivity and improve grounding effectiveness. However, chemical soil enhancement should be used with caution, as some chemicals can be harmful to the environment. It is important to follow the manufacturer's instructions carefully when using chemical soil enhancement products. Regular testing of the grounding system is essential to ensure that it is functioning properly. The grounding resistance should be measured at least annually and more frequently in areas with high lightning activity. If the grounding resistance is too high, the grounding system should be upgraded or repaired. A qualified grounding expert can provide guidance on the design, installation, and testing of grounding systems. Grounding is an essential part of any electrical system. A properly designed and installed grounding system can help to protect people and equipment from electrical shock and damage. When working with electrical systems, it is important to follow all safety precautions. Always disconnect power before working on any electrical equipment. Wear appropriate personal protective equipment, such as gloves and safety glasses. If you are not qualified to work on electrical systems, consult with a qualified electrician. In a specific scenario of a radio tower installation on a rocky ridge with limited soil depth, the design must prioritize maximizing contact area with the available soil and mitigating the effects of the high soil resistivity often associated with rocky terrain. Here's a more detailed look at each of the suggested methods, with considerations for the limitations. 1. Radial grounding system. This involves installing multiple ground rods arranged in a radial pattern extending outwards from the base of the tower. Given the shallow soil, standard vertical ground rod installation might be ineffective. Instead, consider these adaptations. Firstly, use shorter ground rods. Instead of the standard 8 to 10 foot rods, use shorter rods that can be fully driven into the available soil depth. Secondly, horizontal installation. Where vertical driving is impossible, consider burying the ground rods horizontally in shallow trenches. This maximizes contact with the soil. Thirdly, increase the number of rods. Compensate for the reduced effectiveness of each rod by increasing the total number of rods used. Connect all rods with a heavy gauge copper wire, such as number 6 American wire gauge, AUG, or larger, to ensure good electrical continuity. 2. Ring grounding system. A ring ground encircles the base of the tower and provides a continuous grounding path. Firstly, shallow trench. Excavate a shallow trench, even if it's only a few inches deep, around the tower's perimeter. Secondly, conductor size. Use a heavy gauge copper conductor, such as number 4 American wire gauge, AUG, or larger, to form the ring. Thirdly, bonding. Ensure the ring is securely bonded to the tower's grounding bus bar using multiple connections. Fourthly, backfill. Backfill the trench with a conductive material like bentonite or ground enhancement compound to improve contact with the surrounding soil. 3. Plate grounding system. A ground plate provides a large surface area for contact with the soil. Considering the limited soil depth, the typical deep burial of a ground plate might not be feasible. Firstly, shallow burial. Bury the plate as shallowly as possible while still ensuring it is fully covered with soil. Secondly, plate size. Use a larger plate to compensate for the reduced depth. Thirdly, conductive backfill. Surround the plate with a conductive backfill material like bentonite to enhance contact with the soil. Fourthly, multiple plates. Consider using multiple plates connected in parallel to increase the overall grounding area. 4. Grounding rods with extension electrodes. This method aims to extend the reach of the grounding system horizontally. Firstly, radial extensions. Attach copper tape or wire extensions to the ground rods and bury them horizontally, radiating outwards from the tower. Secondly, secure connections. Use exothermic welding or high-quality compression connectors to ensure secure and corrosion-resistant connections between the ground rods and the extensions. Thirdly, maximize length. Extend the horizontal electrodes as far as possible, taking advantage of any available pockets of deeper soil. 5. Chemical soil enhancement. This involves treating the soil to improve its conductivity. Firstly, soil testing. Conduct thorough soil testing to determine the existing resistivity and pH levels. Secondly, appropriate compound. Choose a soil enhancement compound that is compatible with the soil type and local environmental regulations. Thirdly, proper application. Follow the manufacturer's instructions carefully when applying the compound, ensuring even distribution and proper hydration. Fourthly, environmental considerations. Be mindful of the environmental impact of the chosen compound and take steps to minimize any potential harm. 6. Multiple grounding methods. Combining multiple grounding methods can provide redundancy and improve overall performance. Firstly, layered approach. Combine a ring ground with radial ground rods and horizontal extensions to create a layered grounding system. Secondly, interconnected. Ensure all components of the grounding system are interconnected with heavy gauge copper conductors to create a unified grounding network. Thirdly, redundancy. The redundancy provided by multiple methods ensures that the grounding system remains effective even if one component fails. Additional considerations. Firstly, lightning protection. Integrate the grounding system with a comprehensive lightning protection system, including air terminals, down conductors, and surge protection devices. Secondly, corrosion protection. Use corrosion-resistant materials and coatings to protect the grounding system from degradation in the harsh environment. Thirdly, regular inspection. Conduct regular inspections of the grounding system to identify and address any signs of damage or corrosion. Fourthly, grounding resistance testing. Perform regular grounding resistance testing to verify the effectiveness of the grounding system. Aim for a grounding resistance of 5 ohms or less, as recommended by industry standards. Fifthly, documentation. Maintain detailed records of the grounding system design, installation, testing, and maintenance. Sixthly, safety. Always follow safe work practices when working with grounding systems. De-energize all equipment before working on the grounding system. Use appropriate personal protective equipment, such as gloves and safety glasses. Remember to consult with a qualified grounding expert to develop a grounding system that meets the specific requirements of your site and local regulations. They can help you assess the soil conditions, determine the appropriate grounding methods, and ensure that the system is installed correctly. In areas with particularly challenging soil conditions, such as high rock content or low moisture levels, additional measures may be necessary to achieve an acceptable grounding resistance. These measures may include the use of deeper ground rods, chemical soil treatments, or specialized grounding electrodes. The key is to maximize the contact area between the grounding system and the surrounding soil and to minimize the resistance of the soil itself. By carefully considering all of these factors, you can design and install a grounding system that provides effective protection for your radio tower, even in challenging soil conditions. Finally, always remember that grounding is a critical safety component of any electrical system, and it should never be overlooked or compromised. Grounding systems should be tested and maintained regularly to ensure their continued effectiveness.